Hello students, I am Dr. Shilpa K. Gowda, Associate Professor, Department of EC, SJBIT. Today I am going to explain about a field effector transistor. So first we'll start about the what do you mean by FET here, field effector transistor. Like BJT, FET it is also a three-terminal device. These differ from BJT in two respects. Well, BJT is a current control device, but FET is a voltage control device. And also, this voltage control device gives an extremely high input resistance. BJT is a bilateral while FET is a unilateral, which means that only one type of carrier participates in conduction. FET can be used in amplifiers and switching circuits similar to BJT transistors. FETs are of two types: junction field effect transistors and metal oxide semiconductor field effect transistor. There are further subdivided into P-channel and N-channel devices. So first, we'll consider here a N-channel JFET. So in this figure here, the operating principle of an N-channel FET is shown in the figure. A N-type semiconductor material is referred to as a channel is sandwiched between two smaller P-type materials called gates. The end of the channels are drain and the source. The two P-type materials are connected together and forms a gate. And the given gate is not connected to supply voltage and is applied across a drain source terminal. A drain current ID flows as shown in the figure. When gate source voltage is applied, gate negative with respect to source as shown in figure. Due to applied negative voltage, the gate channel PN junctions are reverse biased. The channel is slightly doped than gate material, so depletion regions penetrate deep into the channel. When the depletion region width is reduced due to free charge carriers, they behave as insulators. The width of the depletion region is reduced or narrowed and its resistance is increased and ID is reduced. If a negative VGS is applied and increased further, the depletion regions meet at the center of the channel and ID becomes 0. When an AC signal is applied to the gate, results in increase in reverse VGS that causes increase in level of the signal goes negative. This decreases when signal is positive going up. That is, when the reverse VGS increases, width of the depletion region also increases. This in turn increases the channel resistance and flow of a drain current decreases. When the signal goes positive, the depletion region reduces. Channel resistance also decreases and a drain current increases. If it is gate source voltage controls the drain current. The gate channel PN junctions are maintained in reverse bias so that the gate current is normally low. The IG is lower than the base current for a BJT. The name FET comes from the fact that the depletion region in channel are produced by electric field at the reverse bias gate channel junctions. FET is unipolar because the current flow is due to one type of charge carrier, that is electrons in case of N-channel device. Next, drain characteristics when VGS is equal to 0. We will consider here the drain characteristics with VGS is equal to 0. Figure shows that a circuit for determining the drain current versus a drain source voltage characteristics for N channel with VGS is equal to 0. VDS is increased in steps from 0. ID is recorded for each values of VDS and it produces a table of ID by VDS values for plotting characteristics as shown in figure. When VDS equals 0, ID equals 0 and the voltage drop across channel is 0 and voltage drop between the gate and other points on channel is 0. There is no depletion region penetration into channel and when VDS is lightly increased, a small drain current flows producing some voltage drop along the channel. Thus, penetration of depletion region into channel occurs but it is very small and channel resistance is lesser. Further, increase in VDS, ID increases linearly and channel behaves as a constant value resistance. The channel behaves as a fixed value resistance until the voltage drop along channel causes penetration of a depletion region into channel and channel resistance becomes high. Further, increase in VDS gives a smaller ID and causes a more depletion region penetration with a high channel resistance. Increase in VDS results in no effect on ID and reaches a saturation level. In the graph shown above means a drain source saturation current at ID levels of at IDSS level, it appears to pinch off the channel and the VDS voltage at this point is called as pinch off voltage. And in this region, ID is constant, is known as a pinch off region. So from region VDS equals to 0 to VDS equals to VP, in graph, channel acts as resistance and this part is called as channel ohmic region. If VDS is increased, a voltage is reached to gate channel junction breakdown when this happens and ID increases and device may be destroyed. So the pinch off region is normally operating region for the JFET. Next, drain characteristics with the external bias. So here a circuit is written to obtain ID by VDS characteristics for an N-channel JFET with an external gate source bias is applied. VGS is set to a negative level such as -1 volts. VDS is increased in steps and corresponding levels of ID is noted at each VDS point step. The ID by VDS characteristic for VGS of -1 volt is then plotted as shown in the figure. When -1 volt VGS is applied, the gate channel junctions are reverse bias even when IB equals 0. When VDS is equal to 0, depletion regions are already penetrating to some depth into channel. Because of this, a smaller voltage drop along the channel will increase the depletion region to point where they produce channel pinch off. When VGS equals to -1 volt, pinch off voltage reaches to a lower ID when then VGS equals to 0 and VP equals to 3.5 volts when VGS equals to -1. That is that a family of drain characteristics can be obtained by using several levels of negative gate source bias voltage. If positive VGS is applied, a high level of ID is produced as shown in the figure. VGS is kept negative to avoid the possibility of forward biasing the gate junctions. The dashed line shows the ID saturates for each level of VGS. Since pinch off voltage is 4.5 volts, suppose VGS is equal to -4.5 volts is applied, then depletion regions penetrate so deep into the channel that they meet in middle complementary cutting of ID. So VGS is equal to VP reduces IB to 0. This bias voltage required to do this termed as gate cutoff voltage VGS. So next we have, this is an N-channel JFET consisting of N-type channel with P-type gate regions on each side. Next we have a P-channel JFET. So this is a P-channel JFET characteristics. Figure shows the characteristics of a P-channel JFET. The difference in arrowhead of gate and direction of drain current can be seen in circuit. Also polarity of the supply. The drain is negative with respect to source and gate is positive with respect to source. To obtain the characteristics, VGS is maintained constant at the desired level. Minus VDS is increased in steps from 0 and ID levels are noted at each step. P-channel JFET drain and transfer characteristics are shown in the above figure. So next, this is the transfer characteristics of a JFET. So this is a P-channel JFET characteristics. Next, we have transfer characteristics of depletion type MOSFET. So here in the transfer characteristics of depletion MOSFET, before that we should know that what do you mean by MOSFET here. So MOSFET is a metal oxide semiconductor field effect transistor. So it is a type of FET that has an insulated metal oxide layer between its gate and channel. And also in this there are two types of MOSFET, depletion type and enhancement type. Here both of these MOSFETs are widely used in electronics, integrated and embedded circuits. The MOSFET conducts current between the source and drain. The path for current between source and drain is called a channel, and the width of this channel is controlled by the voltage at the gate terminal. So next we will consider here uh, the types of depletion mode as well as the working of depletion mode characteristics. So in here we have the characteristics of a MOSFET here. So here the characteristics of a MOSFET is similar to that of a JFET. That is, when VGS is equal to 0 volts, ID equals IDSS, and when VGS is less than 0 volts, ID will be equals to IDSS. So this is the circuit symbol of an N-channel enhancement mode MOSFET. So here it has shown the P-channel enhancement mode as well as the circuit symbol. Next we have depletion enhancement mode MOSFET. So depletion enhancement MOSFET means here enhancement MOSFET or E-MOSFET. It is a type of MOSFET where there is no channel constructed during its fabrication, but it is induced in the substrate using the gate voltage. The E-MOSFET does not conduct when there is no gate voltage, that is VGS equals to 0 volt. Therefore, E-MOSFET is also known as normally off transistor. So in this also there are two types, P-channel enhancement mode and N-channel enhancement mode. Thank you.